Hey guys, and welcome to another further Pure 2 revision video. Today we're going to take a look at number theory. It's a brilliant topic. I really enjoy it, and if you're going on to do maths at university, it's a very good topic, and I definitely recommend doing it at uni if you're going to do maths. So let's take a look at the question we've got in here. A mix of questions. I've missed out two topics, so the questions that are the topics that I've missed out are combinatorics and solving congruence equations. So then I'm going to cover them in two separate videos, rather than kind of just trying to throw them in here, because I think they're worth their own videos. So let's take a look at what we've got in here. So question 1 here, or technically it's question 11 in the textbook. We want to find the remainder of this summation. So okay, right straight. So this is the summation now of n factorial from 1 to 50. And it's divided by 21, and we want to find that remainder. So if you're finding the remainder of something divided by, say, p, we take it mod p. So we're dividing by 21 here, which is my p, so we take that mod 21, okay? Now for these questions, you kind of have to spot the trick to it. And it's something that once you've done one of these questions, you know the rest of them, basically. The idea here is, if you consider these factorials, at some point you're going to get to n factorial being congruent to 0, or 21, and therefore every factorial after that will also be 0. So how do we find which one it is? Well, think of the factors of 21. I've got 1 and 21, which isn't ideal. I don't really want to be going up to 21 factorial. So we've also got 7 times 3, 2 primes, right? So we can use that information here now to find out where it stops. And where it's going to stop is at the second factor here, 7, the bigger of the factors. That's where basically 7 factorial and onwards, they'll all be equal to 0. So let's just write down what we've got here. So 1 factorial equal to 1, which is equal to 1 mod 21. 2 factorial, 2 times 1, which is 2 again. That's 6, which is equal to 6 mod 21. 4 factorial is equal to 24, which is equal to 3 mod 21. So this line here, these are mod 21s. That's 120, which is equal to 15 mod 21. 6 factorial, that's 720, which is equal to 6 mod 21, and then 7 factorial here, that's equal to 5005, which is equal to 0. So that's the key point there. Every factorial after this now, they're going to be congruent to 0 mod 21. So all the way down to 50 factorial, which will also be equal to 0. So basically, from 7 onwards, we forget about it then. The question essentially just runs from 1 factorial to 6 factorial. So the reason they're all equal to 0 after this is because they all contain 7 factorial. They've all got that factor here of 7 times 3. So if we add all these up and take a mod 21 again, we're going to get our answer. So 1 plus 2 plus 6 plus 3 plus 15 plus 6 mod 21. So if you add these together, you should get 33. So therefore this is 33 mod 12, mod 21, which gives you 12. Okay, so I'm getting my numbers the wrong way around. So that's equal to 12. So what we've essentially found there is that the remainder is 12. So a pretty standard question there. It's one of them though, once you've done one, they're all pretty easy. So hopefully that one has basically give you the knowledge to do the rest of them of that type. So let's take a look at the next question here. We've got a question looking at the divisibility rules for numbers. So we've got an 8-digit number. So 1, 0, 2, x, 5, 7, 6, and 1. Now we only need to find x. So if the number's divisible by 11, remember you start with your first digit being positive, and then you subtract the next one, then you add on the next one, subtract the next one. So what that actually looks like is 1, take 0, then we add the 2, then we take the next digit, which is x, then we add the next digit, which is 5, so on and so on. So you can see the pattern here, plus 6 and minus 1. So the divisibility rules, I just memorised the the pattern. So you got to do 11, 4 for example, 9. They're all reasonably similar, a couple of little differences, but I don't think it's anything that should be too tricky to memorise. So that's how we do 11. Now, we're testing whether this is divisible by 11. So 11 has to divide the sum of this. So add these up. 8 takes 7, that's 1 plus 6. And then subtract 1, what we should get is 6 minus x here. So we're testing whether 11 divides 6 minus x. So at this stage here now, we have two possible situations. For this to be divisible by 11, 6 minus x has to either be 0, because 0, 11 divides 0 basically, or this has to be equal to 11. Now, we omit one of these, and the one that we omit is this one here at the bottom. And the reason for that is, to get to 11, we'd require a negative number for x. A negative number here, which doesn't make sense in the context of the question. We'd have a negative digit. X clearly has between 0 and 9, okay? But it's just a digit. So therefore, we get rid of that one. We just consider this situation here. So 6 minus x is equal to 0. So x just has to be 6. So in that case, the missing digit is just equal to 6 there. Okay, so hopefully quite a nice easy question. Divisibility rules, they're a good topic. Memorise them, the 3 marks basically. So there we go. Let's take a look at the next one. So this question here is basically an application of Fermat's little theorem. So the part A, we're just asked to state the theorem, and part B is an application of it to find a congruence. So we just need to give the definition basically here. So if we have P, which is a prime number, and we also have A, which is just any integer, and A belongs to the integers, then we can write this as A to the power of P being congruent to A mod of P. Okay, but we've got to be careful here, because if A is not divisible by P, so if A is not divisible by P, then we write this in a slightly different way. So the way we write that is A to the P minus 1 is congruent to 1 mod P. Just got to be very, very careful for that there, okay? But that's just our definition. So it's just basically give the idea of what's going on. So we're just giving the mathematical formula. So then part B, we have to use the application here, or the formula, to show that 2 to the power of 2018 is congruent to 4 mod 5. So with a question like this, first just let's write down what we've got. So we've got 2 to the 2018. So if we want to show that it's congruent to 4 mod 5, we need to take this here, mod 5. Okay? Now we can't do anything with the 2, that would just be congruent to 2 anyway, so we can't do anything with that. So we need to apply Fermat's little theorem here. So that would be 2. So your P here, sorry, is 5. So let's just write this down. So A is my 2, P is 5. So this is 2 now to the P minus 1, which is 4. And the reason we're using this one is we need to check whether A is divisible by P. So is 2 divisible by 5? No, it clearly isn't, right? So we use this formula here, okay? So not this one, but this one. So just always check for this fact here. So now it's 2 to the 5 minus 1, which is 4, is congruent to 1 mod 5. So this is going to be extremely handy. It's going to allow us to simplify this. So we're going to use this now, 2 to the 4, in terms of this 2018. So we need to consider the biggest or the closest number to 2018 that's divisible by 4. Well, think about your divisibility rules for 4 here. For this to be divisible by 4, this has to be divisible by 4, the last 2 digits. Well, 18 is not divisible by 4, so we can't use this. So the closest one here to 18 that would be divisible by 4 would be 16. So the number would be 2016. Okay? If you do 2016, so because this is a power of 4, I need to do 4 times something gives me 2016. So if we divide that by 4, we know what that number is. So that's 504. So then we can rewrite this. So what we actually have now is 2 to the 2018 is equal to 2 to the 4, so 504. So what would we times 2016 by to get to 2018? What would we have to add on? We'd have to be a 2. So we times this by 2 squared. So I'm losing my voice. I'll just quickly take a drink. Hopefully you can finish that for me. See what we get. So, hopefully you managed to simplify it yourself. Here now, there's 2 to the 4. We know that's congruent to 1 mod 5. So, 1 to the power of anything will always be equal to 1. So what I've got now is 1 times 2 squared mod 5. 2 squared is 4. So what I actually have now is 1 times 4 mod 5, which is 4. And 4 mod 5 is just congruent to 4 there, mod 5. So hopefully that was kind of, nothing too crazy. You're just using the application of Fermat's little theorem here. So just writing it out in the correct form, using that fact that it's congruent to 1 mod 5 to then simplify your powers here. So hopefully that's okay. Let's take a look at the next question. A very kind of standard question on the AS kind of exams, where you're given a statement, you want to disprove it. So it's a lot easier to disprove a statement rather than prove it. And the reason for that is you just need to find one counterexample. So there's multiple answers you could actually give here. The easiest probably one, that came to me anyway, if you let A equal 6 and P equal 3, sorry. So if we write this out now, this is 6 to the 3 minus 1. Well, that's 6 squared, which is equal to 36. So if you take 36 mod P, so 36 mod 3, what would we get? Well, 36 is actually in your 3 times table, right? So it's going to be congruent to 0. It's divisible by 3. So this is congruent to 0, which is quite clearly not congruent to 1. Okay? So therefore, we have disproved the statement. So hope that was not too bad. Like I said, there's multiple answers you can give there. Just any answer that gives you something that's not congruent to 1. Happy days, you've done it. So let's just move on to the next one. That was quite a quick one. I've got a question here from the mixed exercise one. So, if you've got 3 to the power of 100, and you want to find the units digit in this number here, how would we do it? Right, if you put this on your calculator, you should get an error, I'm pretty sure, because it'd be bigger than your largest power that your calculator will actually solve for. It does actually give me a digit when I put this on my calculator. Some calculators will return an error, but the number's just ridiculously large, okay? So you're not going to be able to do it in that style. And this is the application of number theory, why we use it. So if you want to find the units digit for a number, so to find the units digit, we take this mod 10, okay? If we take this mod 10, it will give us the units digit. Essentially, we're dividing it by 10. Okay, so what we're doing now is 3 to the 100 mod 10. Right, so where can we go from here? Well, it's one of them. With practice, you will kind of get used to this pattern. If you see a 3 and a 10 here, so you've got base 3, and you're taking something mod 10 here, you should kind of think, jackpot, this is going to be very, very easy to manipulate. And the reason for that is, if we think about how we can rewrite the powers here, well, I could rewrite this as 3 squared to the power of 50. That's just the same expression here. Okay, so these are two completely equivalent expressions. But this is the good part now. This 3 squared, that's equal to 9 to the 50 mod 100. So, sorry, mod 10. So again, still completely equivalent. The good news here is, though, if you consider what happens with 9 mod 10. Well, 9 mod 10, so 9 mod 10 is also congruent to minus 1 here. So we're going to use that fact to rewrite this expression. So this is actually now just equivalent here to minus 1 to the 50. Because they're the same expression, right? Mod 10. So now we can use that fact. Well, minus 1 to the power of 50. So this is just got to be very, very careful here. The fact that this is an even power, this means this will be positive. But obviously, we can't have a negative digit anyway, so we would expect that to be positive. So minus 1 to the 50 is equal to 1. And then if you take it mod 10, it's just congruent to 1 anyway. So therefore, units digit is 1. So that's that question done there. And then finally, the very last question, again from the mixed exercise one, we're just going to do a quick question on the Euclidean algorithm. I've done numerous videos on this, especially involving like Bezo's identity, for example. So this is just a short one, just to throw it in there for a bit of revision. So using the Euclidean algorithm, so what we want to do here is find the GCD of 60 and 4, 4, 4. Okay. So using the Euclidean algorithm now, so using Euclidean algorithm, what we do is we write 444, the biggest number here, and what we're going to do is we're going to consider what happens when we take the 60 into account. So what can we do, or how close can we get using the 60? So what I mean by that is, what's the biggest number I can times 60 by to be as close as possible here? Well, that biggest number is 7, okay? That'll give you 420. You do 60 times 8, we're going to be too big, we've gone past it, so you've always got to be under this number. And I need to add on what my remainder is. So 60 times 7 is 420, so my remainder here is 24. Okay? What we do now is we shift everything along. So everything kind of moves up one. So the 60 moves up here, and then the 24 moves here at the front. So what that looks like is 60 is equal to 24, and then we repeat the same process. So how close can I get with the 24? Well, that would be timesing it by 2. That would give me 48. Times it again by 2. We're going too big, right? So this is 48, and then I've got to add 12 to get to the 60. So my remainder is 12. And then again, shift everything up. So the 24 goes here, and then my 12 goes at the front here. So 24 is equal to 12. What do I times 12 by to get to 24? It works perfectly. The algorithm actually terminates here. Because if I times this by 2, we get 24, and we get left with no remainder. So once you get a 0 here for your remainder, so basically, job done. When I mean job done, we've found the remainder. The greatest common divisor. So, the greatest common divisor is you look at the very previous remainder. So that, in this case, would be this 12 here. So therefore, the GCD of 60 and 444 is equal to 12. And there we have it. So just, again, a very basic question, but it comes up a lot in the AS exam, so definitely something that you should be confident with, and how to find the GCD. So there we have it, guys. That's the end of this one. I hope it's helped. Be sure to leave any topics you want me to run through down below. If you notice any mistakes, because I've been making tons today, please let me know. There's probably one somewhere in here. But I hope that's helped.